Hi everyone, welcome to today's session that is on building a technical support agent with LangGraph. That is a ReAct agent. That agent that actually knows when to stop investigating. That is reasoning plus acting. See, most AI support bots you have seen do one thing. You ask a question, they generate one answer, and you're done. No investigation, no evidence, no follow-up. But today I'm building something different. An agent that behaves like an actual support engineer. You give it a vague problem like my API is returning 500 errors or error 500, and it decides for itself what to check first. Look at the result, decides if it needs to check something else, and only then gives you an answer. So, by the end of this video, you will understand exactly how it is built, tool by tool, node by node, using LangGraph. And we will watch the whole reasoning process live inside LangSmith. So let's get into it. The most important question that comes into the mind is what does what does React mean? What does React mean? React, reason plus act. Basically, React stands for reason, RE is for reason, and act is for act. It is a pattern where instead of asking a language model to answer in one shot, you let it alternate between two things. First is reasoning, and second is act. Now, reasoning is about what it currently knows, what it currently knows, and act. It's usually by calling a tool to gather more information. Then it observes the result of the action. Then it observes the result of the action. And then reasons again. And then it reasons again. And that's the loop. Thought to action, action to observation, and observation to thought again. That is the loop. Now compare that to a plain LLM call. You send one prompt, you get one response, and whatever the model doesn't know, it either hallucinates or admits it doesn't know. But, but, this React agent, this React agent doesn't have that problem in the same way because it can go find out. Like if it needs to know whether the API is actually unhealthy, it doesn't guess. It calls a tool that checks, which you'll understand once I show you the practical implementation of it. Another question that comes to one's mind is that why iterative agents are useful. Why they are useful. The agent doesn't know what it needs to check until it sees the first result. Evidence based answers, not guesses, mirrors how a real support engineer investigates a ticket. But more reasoning steps is equal to more LLM calls is equal to more latency and cost. So here's a key insight. Suppose when a support ticket, when a support ticket comes in, You often don't know what's wrong until you start investigating. If someone says that the app, if someone says that the app is low, you might check application status first. You might check the application status first. If that application status shows high memory usage, then you decide to check the logs. You couldn't have planned that second step in advance. It depended it depended on what the first check revealed until it sees the first result. Okay? And that's exactly why a single giant prompt doesn't work well for this kind of task. An iterative agent can adapt. It reads each observation. It reads, let me be clear over here. An iterative agent adapts. How? It reads each observation and decides in real time whether it has enough evidence or need to dig further, and decides whether it has enough evidence or needs to dig further. So this iterative agent is doing a reasoning rather than doing one shot action and giving the answer. But but this this iteration isn't free. But this iteration isn't free. That is, more reasoning steps, more LLM calls is equal to more latency and cost. So every extra reasoning step is another call to the LLM, which costs time and money. So the goal isn't loop as much as possible, it's loop exactly as much as the evidence justifies. And stop as soon as you have enough. And that balance is what we are going to engineer into this agent through the system prompt and some hard iteration limits. Let's continue. Let's go to another slide. See, the another important thing is the system architecture, the four layers, which are part of this agent. Config layer, model layer, tools layer, graph layer, observability. Now, let me show you the architectural diagram of it. And from that, the things are going to be much more clearer. Now, if you look at this, if you look at this, there are four layers. There are four layers. First one is the configuration layer. Okay. Then you have model layer, tools layer, this orchestration layer, and then in the end, we have observability. But let's first come to this configuration layer. Now, this config layer, That is, it has an env file holding the OpenAI key and LangSmith project settings. Below that, there is a model layer, that is a chat OpenAI instance, which we can then bind our tools to. Okay, which we can then bind our tools to, which we can bind our tools to. Sorry about this. I think my pen tablet is not working that properly. Okay, so where were we? So what I was saying is that this model layer, that is a chat OpenAI instance, which we then bind to our tools, and our tools are check application status, check server logs, check database status, check API health, search internal docs, check container plus. So this binding, which let let the model knows what function it is allowed to call through binding. It lets the model knows what function it is allowed to call. Okay. Now below that there is this graph graph orchestration layer. Graph orchestration layer. Now this is the actual LangGraph state machine that runs ReAct loop and running alongside everything and observability. That is LangSmith tracing, which traces every single call so we can inspect it later. And I'll show you that it has its own UI when we are going to be calling the LLM for any of the queries, and I'll show you the side by side so that you don't feel that LLM is acting like a black box. You can relate with it. It would be more transparent. Okay. Okay. Let's continue. Okay. Okay. Now this is a state graph. This is a state graph with exactly two nodes. One is the agent node, another is the tool node. The agent node over here calls the LLM. It's the reason and decide part. It's the reason and decide part. The tool node over here, it executes whatever function the LLM asked for. Okay, it executes whatever the function the LLM asked for. It is the act part. But between them sits a conditional edge. That is a function called should continue. It, you know, see what it does. It look at the agent's last message and asks, did it request a tool call or did it produce a final answer? Okay, let me write it over here. It looks at the agent's, I think this would be better. Okay. See, so we are basically talking about the conditional edge. So what it does, it look at the agent's last message look at the agent's last message and asks, did it request a tool call or did it produce a final answer? If it requested a tool, we go to the tools node. Okay. If not, we go to end. Now here it would be more clear. If it requested a tool, it goes to the tool node. If not, it goes towards the end. Okay. And critically, the tools node always routes back to the agent. Okay. It always routes back to the agent, and that is the loop. The agent sees the tool's result as an observation and what to do decides again what to do. So here's the complete loop, which is where this project is hinging on. Okay, let me show you another thing. Okay, now this is agent state, that is messages, accumulated messages, and iteration count. Now here what is happening, the messages hold the entire conversation: human message, AI message, tool message, and it uses a special reducer, that is operator.add. And the reason for it is that every node appends to this list. Every node appends to this list instead of overriding it. That's what let us print the full investigation trail at the end. Okay. The second field, that is iteration count, it just counts how many times the agent node has run. Counts how many times agent node has run. Okay, has run. Let's see what is next in the slide. Okay, tool set, 6 diagnostic tools. Now over here, every tool over here is written with LangChain's tool decorator. It's tool decorator. And we have all these 6 of them. The first one is for, it checks CPU, memory, active requests. The second one checks recent error log lines, check database status, it checks connections query time, check API health, endpoint status, error rate, search internal docs, it checks keyword search over docs, and the last one, Docker restart count, exit, reason. But here's the part that actually matters for how the agent behaves. See, the model doesn't know what these functions do from their code. What these functions do from their code. It only sees the doc string. That doc string is the entire interface. Let me show you. Let's go to the code base over here. See, it only sees the doc string because model doesn't know what these functions do from their code. It is only looking at this doc string, and this doc string is the entire interface. Over here. Make sense? Now look at this search internal docs. Its doc string explicitly says use this for known issues, configuration guidance, account support, password reset procedures. That single sentence is what stops the model from going and checking the database when someone just wants their password reset. So, when you're designing a tool for an agent, when you're designing a tool for an agent, this doc string, it isn't a documentation. It isn't a documentation for humans. Okay, it's a decision boundary for the model to act. I hope you're getting me what I'm trying to say over here. Okay, let's continue with the code base and things are going to be much more clear. Okay, or clearer. Let's go step by step now. Let's try to understand this code base and what I've done, and then I'll share with you this Jupyter notebook. Okay, let's start from here. Now this, if you see this particular cell, this particular cell loads our .env file. Where is the env file? Here's the env file. Here's the env file. So this cell loads the env file, and this is where the open AI key and LangSmith credentials live. Here, this is where the credentials live. Now, if you scroll down, now this particular cell initializes the model GPT-4o mini, which I have used. Temperature is equal to 0. See, I'm using temperature 0 because for a support agent, I want the least randomness possible in tool selection. That's the reason I'm using temperature 0. But you can set to 1, 2. But for me, what I want, for that reason, I'm setting temperature 0. Now, in this cell, in this particular cell, I'm doing a sanity check. Okay, that is one plain call with no tools, no graph, just confirming how the model responds. Okay, so I've asked the model that you're a technical support assistant. Respond with one short sentence. What does an HTTP 500 error generally indicate? So it gave me a response that an HTTP 500 error generally indicates the server side issues that prevents the request from being fulfilled. Okay, fulfilled. Now, At this stage, our architecture is this notebook, environment variable, environment variables, chat OpenAI, that's just GPT 4.1, and a plain text response. That is this. That is this. Okay. Now, let's talk about building tools. Building tools. Now, if you see, each of these follow the same shapes. Each of these follow the same shapes. Okay. A Python function decorated with the decorator, that is either a tool, with a doc string that tells the model when to reach for it and return a value that's just a formatted string. Okay. But let's pause on this doc string for a moment. Okay. For a moment. And notice how this check underscore database underscore status says use only when there is evidence of database related problem, not just check database availability. Now this word only is doing real work later when we test the tool selection. Okay. When we test the tool selection. Okay. Then we have check API health, then this tool, search internal documentation, check API health tool, search internal documentation tool, check container status tool. Okay. Now this cell combines all six single tool list, into a single tool list, which is what we will hand to the model next. Okay. Now let's check this one, that is binding the tools. See, check this one, llm.bind underscore tools. Now the model knows the full list of functions it is allowed to request, because tools over here and then tools are binded over here. llm.bind underscore tools and tools. So the model knows the full list of functions it is allowed to request. Okay. Now, before even I built the graph, I did a sanity check tool. I did a sanity check tool selection directly over here. That again, you are a technical support agent. Customer question: I forgot my password. How can I reset it? Select only relevant tools. Do not inspect infrastructure unless necessary. I asked. I simply asked a password reset question, and I want to see search internal docs. Search internal docs as a tool call and nothing else. So when I ran this command, what I got was search internal docs. Okay, no database check, no API health check. So that's the whole point. That's the whole point. The agent, the agent should not call should not call unnecessary tools. So it is doing some kind of a reasoning, some kind of a thought process. Okay. So after running, I got this output. Search internal docs. Okay. Let's continue. And then I'll share you this code you can run and things which be much more clearer. In the next project, I'll show you the modular coding. Okay. The complete app-based project on Streamlit or Next.js. But here, I wanted to make you understand how this particular agent works. Now here, we are on agent state and system prompt. Okay. Now, this agent state, this is very important. It stores all conversation messages. Operator.add appends new message instead of replacing the old ones. So this is a shared memory of the graph. Shared memory of the graph, which means that it is going to store all the conversation messages and it's going to add all the messages rather than replacing the old ones. Okay, a kind of a memory. Okay, like I remember the previous day conversation that I had with someone and the another previous day conversation I had with some other guy. So that is my shared memory. Okay, okay. Now this cell, system prompt cell, this is the most important cell in this whole notebook. This is where the actual behavior policy lives. It tells the model in plain language five rules. Five rules. Use tools when relevant. Don't call unnecessary tools. Investigate iteratively. Only continue when the previous observation gives you a reason to. And don't wander into unrelated infrastructure. Unrelated infrastructure. Then it gives workload examples. For such scenario, we support, and finally it specifies the shape of the final answer, that is problem identified, evidence collected, recommended actions. Okay, then let's come over here. Okay, agent node and the tool node that I showed you in the architectural diagram. Now this agent node over here is a small function. It takes the current state. It takes the current state, prepends the system prompt to message history, calls LLM with tools, and returns the response plus an incremented iteration count. Now, that returned AI message is either going to contain tool calls or it's going to contain the final answer text that I showed you in the architectural diagram. If it requires another tool, it will call that another tool, or if it doesn't, it will just call the final answer. Okay. Now, on this acting side, that is the tool node, it is a pre-built LangGraph component. It reads Whatever tool calls the agent requested, runs them, and converts the result into tool message that get back into the conversation. Okay, let me explain you that again. See, this tool node, okay, it reads whatever tool call the agent requested. Whatever the tool calls the agent requested, okay, runs them and then converts the result into tool message objects. Now these tool message objects get fed into the conversation. Okay, conversation. Now I have also turned on this handle underscore tool underscore errors is equal to true. So if a tool throws an error, okay, the graph doesn't crash. It turns the error into a message the agent can react to. The agent can react to. I hope you're understanding this point as well. Okay, now uh, let's come towards building and compiling the graph. Building and compiling the graph. Okay, now look at this cell. Look at this cell. Now, this is where everything we have discussed becomes an actual graph. To to add underscore node. Now, to add underscore node calls the these calls register our agent and tool functions. Okay. Wait, I think something is missing. If I have not agent node tool calls tool node tool result and yeah, it's okay. Yeah, not a problem. Yeah, not a problem. Anyways, okay. So what we are talking, I was saying that there are add nodes, two add nodes. Okay, one is for our agent and one is for our tools. Then we have edges, four edges. Okay. Now start always goes to the agent. Start always goes to the agent. Then the agent's outgoing edge is conditional. That is conditional, and that is decided by should underscore continue. That I showed you in the architectural diagram. I'll show you that again. Okay. Then after that, tool always routes back to the agent. Tool always routes back to the agent. Okay. See, mm, if I go to the okay, see, let me repeat this again. Two nodes we have agent node and the tool node. Okay. Then we have edges. That is start always goes to the agent. Okay. Then we have conditional edging. Conditional edging that is should underscore continue function. Okay. Now over here, if it needs to call a tool, then it will call the tool node. If not, then it will end it. Right? This is what we discussed. Right? But according to that state graph that we have compiled, now what happens? This tool routes back to the agent. Okay. And then we call a dot compile, we call a dot compile, builder dot compile, okay? And now we have a runnable LangGraph object. This is a simple version of that. Start agent tools. If there is something it want, it want to call another tool, it calls the tool, it goes back to the agent. This circular reasoning and thinking and activity of these two goes together, and then in the end, if it wants to come up with the final answer, it produces the final answer and then end. Okay, then end. But here's a catch. Here is a catch. This iteration costs a lot sometimes. So we have to implement iteration protection over here. Iteration protection over here. Now, if we scroll a bit more, these are just the sample examples that I ran and got the results of it. Once I'll share uh, this file with you, you can run it by your own and will come to know what exactly happened. But it's the main majority of the overview that I'm giving it to you. It's the most of it I have already completed with you right now, but rest of it, once you try by your own, you'll understand. Okay, so where were we? We're talking about the iteration protection. Okay, here we are. So what is iteration protection? First of all, what is an iteration protection? See, an LLM doesn't always know when to stop. Sorry about that. I think some problem with that. Okay. See, LLM doesn't know when to stop. Okay. It could keep saying, let me check one more thing indefinitely. And every one of those checks costs time, money, and API calls. Right. So I added independently a safety net. That is, max iterations is equal to 5 over here. Max iterations is equal to 5. That is, track through the iteration underscore count field. Track through the iteration underscore count field. It's checked first before anything else. Inside should underscore continue. If we have hit 5 agent calls, we stop. No matter what the model wants to do next. Okay, so this is fixed. If this iteration underscore count is greater than or equal to max iteration, suppose this is 6 and this is 5, it ends over there. Okay, it just stops. So maximum iterations are allowed 5. So that circular looping only goes till 5 unless it gets what it wants. Not unless it gets what it wants, because that would be, sorry for that, because it would be continuously going forever. So we don't want that. That's why we have said this max iterations is equal to 5. Okay, now let's run a live scenario. Okay, let's run a live scenario over here. Let's say, mm, and then I'll show you LangSmith. Let me check if I've opened the LangSmith as well or not. Yeah, right. Okay. So suppose my API is returning HTTP 500 errors. Okay, let's hit this and let's go to the LangSmith. Mm, okay, okay, I think, yeah, this is the latest one, I believe. Right, okay, let's let's discuss this first. This is the input. Okay, my API is returning HTTP 500 errors. Okay, so see the first iteration is the agent decides to check API health. Okay, that's the most directly relevant tool. The result comes back as okay, that is much more clear. The result comes back as unhealthy HTTP response 500 error rate 42%. Okay, on the second iteration, rather than stopping, the agent notices it still doesn't know why the API is unhealthy. So it checks the server logs, right? It checks the server logs. Then that returns the database connection timeout error. Now it has two pieces of evidence: an unhealthy API and a database timeout in the logs. And it decides that's enough to answer. Again, it has two pieces of evidence. It has two pieces of evidence. Okay. Sorry about my writing. I'm still figuring out it is working. Two pieces of the evidence. Okay. One is unhealthy API, unhealthy API, and the another is the database connection timeout. This one. Okay. And it decides that's enough to answer. It stopped calling tools and gives a final recommendation. See, here is the recommended action. Okay, investigate the database connection setting and ensure that the database is operational and accessible. Check for any network issues or resource constraints that may be causing the database connection timeout. Consider reviewing the application code handling the API requests to ensure proper handling and logging for better diagnostic future. Okay, structured exactly the way our system prompt asked. Problem identified, evidence collected, and recommended actions. Okay, okay. But did you notice one thing? You know, it touched this check API health and check server logs, but it didn't touch the other tools. application status, never check the Docker container, never search the docs. Only two targeted tool calls: check API health, check server logs, and the grounded answer over here shown in LangSmith properly. So it's not anymore a black box. It's very transparent and it is showing what has exactly happened. Okay, what has exactly happened. Okay, so what are the key takeaways from this session, from this agent that we have created, the reason and act agent? What are the key takeaways? First, a ReAct agent is a graph with a loop. Is a graph with a loop. One node reasons, one node acts, a conditional edge routes between them, as shown in the architectural diagram and practically. Second, tool doc strings. Tool doc strings. These are prompts. These are prompts. They directly control what the model will and won't call. What the model will and won't call. Third, third, operator dot add. Operator dot add. This accumulate conversation history. Accumulate accumulate conversation history across loop iterations automatically. Then unbounded agent loop. Unbounded agent loop. These are real risk. So implement an application level iteration budget. Okay. The I'm talking about the iterative protection. Unbounded agent loops. These are like, running like anything. And that was application level iteration that I said. Okay. Then last but not the least, tracing isn't optional. Next time I'm going to be using pen tablet, I believe. Sorry, iPad. Tracing isn't optional. Okay, and that I've shown you through LangSmith. It turns a black box into an inspectable execution tree. Okay, so to recap, a React agent is really just a graph with a loop, reason, 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 act, observe, repeat. Okay, so React agent is really just a graph with a loop that is reason, act, observe, repeat until the evidence says stop. Okay, so this was React. So you have built an agent today which has its own thought process, reasoning, acting, observing, you know, a very smart agent you have built today. I'll share you the codes so that you can run by your own and do your own practical. implementation and get hold of it. Next time, I'll build an agent in a proper app format so that you can see how the agent is working. Maybe some different kind of agent, not React. Okay. So I hope this was useful and you have genuinely learned something new today. And if this video helped you, I would request you to make this video reach to more people. And if you want more of this agents building breakdown, agent building uh, implementation or agent building breakdowns, subscribe to this channel. So see you in the next session. In the meantime, happy learning and good night.